Welcome to Introductory Earth Science Lab. Today we will be discussing oceans, waves, and tsunamis. We will explore how waves are created, the different types of waves, how tsunami waves are formed, and how they differ from regular surface waves. Most waves are created by wind affecting the surface and the surface currents that run through the ocean themselves. The motion of these waves is referred to as orbital motion, which is the concept that individual water molecules are not carried along by a wave, but follow a circular path or an orbit as the wave energy moves through the water. Take a look at the animation on this slide. Notice the largest orbit is the closest to the surface, with each one below becoming progressively smaller as the depth increases. Eventually, there is no longer orbital motion, and the orbital energy at a certain depth is effectively zero. The depth the orbital energy reaches zero is referred to as the wave base. All waves have basic parameters that can be measured. Understanding the basic features of how a wave works lets us calculate other wave properties and characteristics. A wave generally has four parts: the crest, the trough, the wave height, and the wavelength. The crest is the point where the displacement of water is at a maximum, or the peak of the wave. The trough is the point where the displacement of water is at a minimum, or the bottom of a wave. The wave height is the distance between the crest and the trough. The wave length is the distance between either two crests or two troughs. We can calculate wave parameters based on these measurements. The period of a wave is the length of time between the passing of one wave crest to the next, usually measured in seconds per wave. The frequency can be calculated as the number of waves per second and measures the rate at which waves pass a point. We can calculate wave speed by taking the wavelength over the period to determine how fast a wave is traveling. Here we see a diagram of the wave labeling the different parts that were just discussed. Notice the trough and crest are not established from sea level, but rather from the actual dimensions of the wave, as is the wave height. Wavelength is more commonly measured from crest to crest, as shown here, because it is visually simpler to pinpoint that than the troughs when observing waves in the ocean. These parameters can be used to better understand the difference between deep and shallow water waves. Deep water waves are waves in which the water depth is greater than half of the wavelength. For example, if the wavelength is 10 meters, the depth of the water must be more than 5 meters. Deep water waves often have short wave heights and long wavelengths. They will not interact with the seafloor, as the orbital motion we previously discussed will dissipate before the wave base reaches the seafloor. We can calculate the theoretical velocity for deep water waves by multiplying 1.25 by the square root of the wavelength. This can be used to calculate the required velocity to have a deep water wave based on the depth of the water we are in. Shallow water waves are waves in which the water depth is less than half of the wavelength. They often have short wavelengths and tall heights. In this case, the wave base would be deeper than the water depth, causing the orbitals to contact the seafloor. The friction with the seafloor changes the orbital motion, and as a wave progresses towards the shore, the waves begin to bend along with the shape of the seafloor. Friction will cause a decrease in wave speed, a decrease in wave length, and an increase in wave height. This process is what causes a wave to crash and break on the shore as the water depth shallows and friction affects the wave parameters. Eventually, the wave becomes too large in height and it breaks or crashes, as I'm sure we've all seen on the shore of a beach where the waves break. Tsunami waves are not the same as tidal waves, or the type of waves we just discussed that are generated by wind and surface currents. Tsunamis are massive waves that displace large volumes of water, and often with catastrophic results. Tsunamis are considered the secondary effect of an initial natural disaster caused by the displacement of water, including disasters such as underwater earthquakes, volcanic eruptions, landslides, glacial calving, and even meteorite impacts. Tsunamis are considered shallow water waves due to their large wavelengths, some of which have been recorded at over 300 miles long. For this reason, Tsunami waves are almost imperceptible in deep waters. While they often record high wave speeds between 300 and 600 miles per hour, the wave period is often greater than 10 minutes and can be up to 2 hours. When a tsunami reaches shallower water, friction slows down the wave speed in the same way as shallow water wave approaches the shore. However, since the wave speed is much higher than an average shallow water wave and involves the movement of a larger amount of water, the energy from the speed is vertically displaced, which causes the wave height to increase dramatically, known as the shoaling effect. This animation should give a basic idea of how a tsunami is created and what kind of damage it can cause. There are many factors that affect the severity of a tsunami wave, including the magnitude of the earthquake, size of the landslide, eruption of a volcano, how big or how small it is, the distance from the epicenter of the earthquake, the volcano, or the landslide, the slope of the sea floor as the wave approached land. A more gradual slope will create a bigger wave, as the waves have more time to develop and be affected by friction. If the slope is too steep, the waves will simply break and the tsunami will cease to exist. How many waves reach land will affect the amount of disaster that is on the land and protection from other landforms, known as the shielding effect. You can see on the map here, Australia is very well shielded by New Zealand and Indonesia and other islands in Western Asia that keep them sort of safe from volcanoes and earthquakes from those plate boundaries. They hit those landforms first, as opposed to hitting Australia. The Pacific Ocean itself is the most active tsunami zone, as it is surrounded by what's called the Ring of Fire, a string of volcanoes on the Pacific plate boundary. There have been recorded tsunamis in the Caribbean and the Mediterranean seas as well, but the Pacific is by far the most active. Tsunamis are a threat to many coastal areas, and in order to effectively mitigate any potential disasters, the National Oceanic and Atmospheric Administration, or NOAA, has developed and deployed Deep Ocean Assessment and Report of Tsunami, or DART, buoy stations. The stations allow scientists to access real-time oceanographic data that can detect tsunamis and provides a better warning system for the people that live in coastal areas. Other countries, such as India, Thailand, Colombia, Australia, and Chile, to name a few, have their own system of alert buoys in order to help keep their coastal residents safe. There are structures such as artificial reefs, underwater barriers, floodgates and channels, and walls that have been created to help slow the advancement of a tsunami wave. If you live near the coast, it is best to be prepared. Stay informed, listening to warning systems, have a plan and a disaster kit, and be ready to leave in case of an emergency.